negative numbers in binary. Start with data representation. So imagine that you are the person who invented computer, and you are thinking about how can I represent negative numbers in computer. Just all the numbers are binary, just 1 and 0s. And you can think about, what about we add 1 digit in the very front on the MSB as an MSB, so let the computer know the MSB will always be the sign bit, but not the real data. So probably we can use 1 as a minus sign because it's a bar, but just vertically, not horizontally, right? We just use 1 as a minus sign, but 0 as a positive, as plus. Okay, so that's what people did in the very beginning, right? But they found a lot of problems. That's why they didn't use it anymore. So probably when people invented the computer back to 1960s, 1950s, they were trying to use this kind of number system, use the MSB as a sign bit. But after they find a lot of problems, so in the modern devices, nobody are still using the MSB as a sign bit anymore. But now we still have examples and see why that's a problem. Data representation. You have unsigned and signed, 2 types of binary numbers. So for unsigned, this is what we just learned last week. So like the 01001, we just never care about the sign. So what is this? This will be 5, and this will be 5 as well. Right? We just never care about the signs. So for the signed, we use MSB as a sign. So for example, so here, let's just write it down. For the signed version, so this is 5, and this is minus 5, because this digit is being used as a sign. So that's a minus sign, that's a plus sign, that's positive 5, that's minus 5. But there will be a problem. So what's the problem? How would you know? Yeah, the computer can recognize actually. So you just usually use a MSB as a sign bit. They are able to find that. So because every digit is controlled by a transistor, right? So you can always sense that. That's not a problem. But the problem is you are having. So what about this? You have 2 binary numbers, right? But what are they? Yeah, that's this, right? And that's this. So that's a problem. So that's why people don't want to use this anymore. Okay. And there's another one called 1 complement, another version. It's called complement. So the concept of the complement is, for example, I just give you some examples to in decimals. For example, 10's complement of 5 is what? 5. So 10's complement of 6 is 4. 10's complement of 1 is 9. That's just a concept, okay? So when people are saying that's 10's complement, so that's a name. It's not saying 10 itself, the complement to 10, not like that. It's just a name, 10's complement, right? So that's the name of that. So 10's complement of 5 is 5. 10's complement of 6 is 4. So for complement, in the beginning, people are saying, what about that? We have a binary number and we invert every digit, and that number will be the negative version of that number. What about that? Will that work? So this is called 1's complement. The reason is, if you have 0101, so what's a 1's complement of that number? You just use 1111, so 1 at every single binary digit, subtract the original number as a that digit for that number. So for 1's complement of this guy will be 1111 minus 0101. So it's just 1's complement to every digit. It's 1010, right? Yeah. I think probably 40 years ago or something, people are still using, some of the systems are still using 1's complement to do some of the work. So 1010, that will be the minus version of that number. For example, this is 5. So let's use this number as minus 5. You know, it's just let the computer, you just make a lookup table in the computer. Just let the computer know, hey, this is a positive number. These are all the negative numbers. So now here's a problem. So what if, so what about this? 0, 0, 0, 0, and 1's complement is 1111, right? So you have two binary numbers. You have two different binary numbers are actually representing the same number. And what is that? That's 0, and that's something is minus 0 or something, right? But they are the same number, but you have two binary numbers. Sometimes can cause some problems. So that's why finally people start trying to use 2's complement, which are being used in every digital device like your laptop, smartphone, and computers. They are all 2's complement. And we can verify pretty soon using a calculator. So what is 2's complement? So let's start with the concept. So concept. For definition. So this is how you get the definition of 2's complement, but in a real life, I never use that for calculation. But you need to know where does that come from. So 2's complement, for example, we have 0, 1, 0, 1. We know this is plus 5. It's also plus 5 in 2's complement, no problem. So what's minus 5 in 2's complement? We actually use 1, 1, 1, 1 minus 0, 1, 0, 1. That's the first step, right? That's the first step to get the 1's complement first, which is 1, 0, 1, 0. And then we plus 1 to that number, which is 1, 0, 1, 0 plus 1, which is 1, 0, 1, 1. And that number is called 2's complement. Of that number. And we define this number is minus 5. Have we ever learned this before? No. Okay. So that's by definition. If you convert a positive number to a negative number in this way, you'll never get a problem. So invert it, invert every digit, invert and plus 1. Remember in this way, invert and plus 1, invert plus 1, invert plus 1 will be the 2's complement. So let me know 1011, what is that number? You don't know? So what about this? In 2's complement. So right now we are talking about everything to 2's complement. So what is this number in 2's complement? So for the positive numbers, it's not changing at all. It's the same concept that yes, 1011. It's still 1011 in the unsigned binary number, as we learned last week. But we put a 0 in the front, so which means it's a positive number. It's a positive 2's complement number. So what is that number? So what is this? 8. What is this? 2. What is this? What is this number? Positive 11. So what's minus 11 in 2's complement? What's minus 11 in 2's complement? Remember here? You have a cheat sheet here. Just move your eyes. Just move. Invert and plus 1. That's it. Yeah, invert and plus 1. So invert it first. 1, 0, 1, 0, 0. Plus 1. 1, 0, 1, 0, 1. That's minus 11 in 2's complement. That's really hard. And there's a very easy way to do 2's complement in the future. I will tell you later. I invented. Not now, but just introduce a definition for here. Seems like it's really hard. I have to invert and plus 1. So now I give you another number, 1, 0, 1, 1. You actually couldn't tell. Your brain could not resolve it. What is this number in 2's complement? You don't know. Do you know? You don't know. You have to convert it back. How to convert it back? Minus 1 invert, right? And then you'll see the positive number, and then you know what that minus number is. Can you get that? So minus 1, you got 1, 0, 1, 0, and invert it. 0, 1, 0, 1. So what is that? 5. So what is this number? Minus 5. So keep in mind, your brain, at least my brain, cannot resolve this number without any calculation. I don't know. I don't know what is that. But I will let you know one technique can get that number really quick later. But now you couldn't tell, right? Can you tell? If I give you, for example, 1, 0, 1, 1, 1, can you tell what is that? You cannot. You cannot. You have to convert it back. How can I convert it back? I'm repeating. So how can I convert it back? Minus 1 invert. So see the positive number, and you know what's the absolute value of that number. Just add a minus sign in the front. You know it's going to be the minus that one, right? And how can I convert a positive number into a 2's complement? Invert and plus 1. How can I convert it back? Minus 1 invert. Do you get that? Okay. Think about it one more time. Give you more examples. All right, yeah.
Do you know that you're working in this 2's complement space and you need to apply these additions and inversions?
Yeah, I will let you know in the problems.
Okay, so it's not something you can look at the number and whether you read it or...
No, it's by definition, totally by definition. It's not that, so for this one, definitely, if it's a binary number, it is not minus, I don't know what is that. So for example, this one, it's not minus 5 at all. Is it minus 5? It is not. What is this? It's 11. In unsigned binary numbers, like what we learned in the first week, it is 11. It's not minus 5, because we don't have any other way to represent negative number in the computer. So we have to, assign part of the numbers into probably 50% of the numbers into, just assign them, just let people know these are negative numbers. It's all by definition. So we did that. It's not defined by the God. It's totally not. It is not minus 5, right? It's not. We just define, we force this one to be minus 5. So now here's a way to calculate. You agree with that, right? You couldn't tell what is this number is. You have to do what? Minus 1 invert. All right, repeat. So I'm going to let you know one way to find out what is that number is. 10111, still this number. Okay. So all the rest of the numbers except for the MSB, all the rest of them, you just think about these values are positive values. So what is it? Just don't look at this. If I give you a number in 2's complement, don't look at this. What is this number? 7. However, in 2's complement, you treat the MSB as a minus value, as a negative value. But you still use the absolute value as that digit. What is this value here? Absolute value. 16. However, it's not 16 in 2's complement, it's minus 16. Why? So that's the way you can know what is this 2's complement is super quickly. That's a magic in there. That's a secret, right? Remember that. So whenever you see a 2's complement number like that, this applies not only to someone have an MSB to be 1, but also MSB to be 0. It's the same concept. 0 minus 0. Sorry, I muted. I muted. Why? And then add them together. That's a real 2's complement number. What is this? Minus 16 plus 7. What is that? Minus 9. Can we verify that in 2's complement definition? How to verify that? One more time. Minus 1 invert. So minus 1, 1, 0, 1, 1, 0, right? Invert 0, 1, 0, 0, 1. Is that 9? Is that magic? You don't need to do this anymore in the future. Is that easy? 1, 1, 1, 1, 1. What is that? It's minus 1. No, let's start. Don't start from there. Let's start from. What is this? So what is this number? It used to be 2, right? It used to be 2, but in 2's complement it's not 2. What is that? Minus 2. What is this? It's still 1. So what's this number in 2's complement? Minus 1. What about this? What this number used to be? It used to be 4. But right now minus 4. What is this? What is this? What's final result? What is this? -1. Wait, what is it? Yeah, I know, but what is this? -8. What are they? 7. What is that? And why? And why is that? In 2's complement, why is that? Intuitively, still, why?
Everything's going to go to 0 except for the last digit, and then you just want a negative up front.
Yeah, that's from the definition, but intuitively, why is that? So this number is all the other numbers plus 1. And that guy is minus. That's why. All the rest of them add together, you get a number has an absolute value which is 1 less than this digit. You agree with that? Because all these numbers plus 1 you get a carry, which is this guy. But this guy is minus. So you got a minus 1, always. Right? What's this? Wait, come on. In 2's complement. What is this?
-2.
So what is this? What is this?
-2.
So what is this? Why is that?
Based on the same principles that we just talked about.
Yeah, so same concept, right? So this number and this number, so what's the difference, absolute value difference? 2. It's always -2. So we get a conclusion here. So whenever you're adding ones in the front, for 2's complement, you are not changing the value. You can add a million ones in the front. It's not changing the value. And now let's verify. Since we know the laptop is using a 2's complement system, see if that's right. And we are verifying our consumption, our hypothesis from a real device in the real world right now. So we convert it to programmer. See all this. I'm sure you can do it here, but I'm not letting you know that you can do the homework in this way. Okay? When you're converting numbers, you need to show the process to get a credit. If you directly put a number in there, you got 0. Is that clear? Okay. So, what you want to use? So for some binary, okay? I put a 1, 1, 1, 1, 1, 1, 1. No. Let me see. How can I do it? Let's do it in decimal. So if I do a calculation, you can see what's the binary number here will be. So if we do, so we want to, for example, we want to get a -1 as a result. So let's use 5 minus 6 equals to. Did you see anything? You didn't see what I'm doing? Did you see what I'm doing? What does bin mean? It's not mean trash box, trash bin or something. It's binary, right? So how many ones you have here? You think, don't count, just think about it. Wait, is that 64? Why 64? That's a 64-bit operating system, right? So every single digit represents one binary memory in the computer. And how many ones you have? 64 ones. And is that -1? It is -1. So that's, you see -1 in the decimal version, and in the binary version, it's going to be this. It's just super little number, but you see how many ones, how many transistors are being turned on in there. Just on. Right, 64, a lot of power. So let's try another one. 5 minus 7. Let me know the answer in binary. 5 minus 7. What's the answer in binary? 1 0. Where's the 0? LSD, right? Yeah. See? And at least we know this laptop is in 2's complement, not 1's complement, right? It's a 2's complement computer.
What would still run on 1's complement?
I don't think so.